I would now like to consider routes that chemists use to synthesize amines, specifically to be able to synthesize more complex amines. You generally have to start with something that contains the nitrogen in it, and that something that you frequently start with is actually ammonia. So the most obvious route towards the synthesis of an amine would be a nucleophilic substitution reaction. Okay, so you could, for example, treat ammonia with an alkyl halide, and we have seen some examples of this reaction actually being successful. So initially, the ammonia will do an SN2 reaction on ethyl bromide, for example, and since ammonia is a neutral nucleophile, you will end up with a molecule with an intermediate initially that has a positive charge on the nitrogen. When we have drawn mechanisms for this process, another molecule of ammonia comes in, removes the extra proton that's on the nitrogen to give neutral ethylamine. And can you make some amount of ethylamine this way? Yes. But the problem is, you see, now that we're getting into second semester, we're going to look a little more at the nuances of this chemistry. The problem is, what is to stop ethylamine from being a nucleophile and continuing to react with more ethyl bromide? And the initial product of this will be also have a positive charge on the nitrogen. It now has 2 ethyl groups on it. And then this can continue, get deprotonated, and make diethylamine. Well, the answer is there's nothing to stop that from happening, and it will keep happening. So the nucleophilic substitution reaction, while it may seem beautiful on paper, in practice leads to a mixture of alkylated amines. In fact, this reaction will often continue until you no longer have a lone pair on nitrogen or any more hydrogens on nitrogen to react. So you can actually end up with tetraethyl ammonium bromide, which is called a quaternary ammonium salt. So not a great synthetic route for amines. What I'd like to do in the rest of this lesson is go over a couple of reactions that are more synthetically useful that can produce just a desired amine in high yield. Okay, and the first one of these is called the Gabriel synthesis. And in this case, instead of starting with ammonia in terms of trying to do the substitution with an alkyl halide, you start with this molecule called phthalimide. Okay, that's a somewhat unusual beast. An imide, I-M-I-D-E, is the nitrogen analog of an anhydride. So it's got a nitrogen between 2 carbonyls, but being a nitrogen, it has a hydrogen on it. And this nitrogen is part of a diamide. It is between 2 carbonyls, and therefore that lone pair is incredibly resin stabilized for the reasons we talked about 2 lessons ago. So phthalimide is not going to be appreciably basic at all by itself. In fact, it turns out that it is acidic. So the first step of the Gabriel synthesis involves deprotonation of phthalimide with KOH. So this hydrogen that's alpha to 2 carbonyls and on a nitrogen has a pKa of about 9. So it is deprotonated completely and rapidly by KOH. This now gives the anion, and this anion is a good nucleophile, the potassium phthalimide anion, and it reacts with an alkyl halide, and this puts the R group onto the nitrogen, forms the important carbon-nitrogen bond. So now, in order to get an amine out of this, RNH2 is what we are after, we need to remove the fragment we want from the phthalimide piece. And we actually do that by reacting the N-alkyl phthalimide with hydrazine, NH2NH2, and that comes in binds to both of the carbonyls, probably in sequence over several steps, releasing the amine and replacing it with the phthalazine 1,4-dione. And that reaction with hydrazine is very good because hydrazine is having two nitrogens on it is a very nucleophilic amine. Okay, so that's the Gabriel synthesis for you. So literally you take phthalimide as your nitrogen atom source, and phthalimide is actually quite cheap. Deprotonate, alkylate, react with hydrazine. 3 reactions will get you just the primary amine you want in high yield. But suppose you don't want a primary amine. Suppose you want something that's a little more substituted. Well, the most common reaction that's probably used as a general amine synthesis is called reductive amination. And to understand this reaction, you need to first recall that if you react either ammonia or a primary amine with an aldehyde or ketone, we will get an imine. Okay, so in this case, we have a ketone reacting with ammonia, and that's going to give you an imine with a hydrogen on it. Well, if a reducing agent is present, that imine that I drew there is actually not going to be a particularly stable imine. That imine formation is going to want to go in the opposite direction. But if you can reduce it, the imine can be reduced in situ, which means in the reaction flask, in order to form an amine. So in this case, we are forming a primary amine. So the reducing agent that we commonly use is called sodium cyanoborohydride. Okay, you've already learned about sodium borohydride, so this is a close cousin of it. You've also learned about lithium aluminum hydride. This is a more distant cousin of lithium aluminum hydride. So the reason we use sodium cyanoborohydride rather than regular sodium borohydride is that the CN group is an electron withdrawing group, so the inductive effects of the CN group make the sodium cyanoborohydride a less powerful hydride source than sodium borohydride. So it's actually only going to reduce the imine and not reduce the aldehyde or ketone. And that's important because, as I said at the top of this slide, the imine formation, of course, is a reversible reaction, and you're not going to have quantitative conversion of your aldehyde or especially your ketone to the imine. If the aldehyde or ketone gets reduced to a secondary alcohol, it is no longer capable of reacting with an ammonia or an amine to form an imine. So we need to make sure that we just reduce the imine and not reduce the aldehyde or ketone. Sodium cyanoborohydride is such an unreactive hydride source that we actually do these reactions under weakly acidic conditions. Regular sodium borohydride would react immediately with acid and get destroyed, but doing these reactions under weakly acidic conditions, first of all, favors the formation of the imine, but actually, if you think back, one of the intermediates in imine formation, right before you get to the imine itself, is an aminium ion, where you still have a hydrogen on the nitrogen and a positive charge. So the aminium ion is actually more easily reduced. The carbon is more electrophilic than the imine itself. So evidence basically points to the fact that the aminium ion is what gets reduced by sodium cyanoborohydride. So you have the hydride source, you have the amine, you have the acid, and you have the aldehyde or ketone, and you just mix all of them together in the same reaction flask. Doesn't matter what order you put things together, and that gives you the amine products that you want. So some of the examples I have depicted on the slide here, if you use ammonia as your amine, you will get a primary amine out of this. If you use a primary amine as your amine, you're going to get a secondary amine. And if you use a secondary amine, you're going to get a tertiary amine. So in all cases, yes, you may need to start with an amine, but reductive amination is a reaction that takes a simpler amine and turns it into a more complex amine product. Okay, so Gabriel synthesis and reductive amination are two reactions that can be used to synthesize amines, desired amines, selectively in high yields. Okay, so that's our introduction to amines, and what I want to do next is look at a very specific type of amine, which is called the amino acid, that is more biologically relevant. In the course of our lessons on amino acids, we will learn one more of these quote-unquote name reactions, namely the Strecker reaction that is used to synthesize amino acids.